So good day everyone. So now, Miss Sandy and I, we're going to talk about an important concept of optics, the resolution in its relationship to diffraction. But first, let us understand what resolution means. So as stated here, resolution, it refers to the ability to distinguish between two closely shaped objects or details. In imaging system, higher resolution means finer details are visible. The smaller the resolvable distance between 2 points, the higher the resolution. So in order for us to visualize or to understand what resolution is, take a look at this diagram and imagine yourself looking through a microscope or a telescope. So the resolutions is the ability of that instrument to distinguish between two objects that are close together. And if the objects are too close, they might seem as one instead of two. So basically, resolution is it's about how clearly we can see in details. Now, here is the interesting part, because even best lenses and mirrors has a fundamental limit in their resolutions, and their limit came from something called diffraction. I know we are all familiar about what diffraction is since some of my classmates already discussed about it. So as stated here, diffraction is the bending or spreading of waves like light or sound as they passes through an aperture or opening or around an obstacle. This bending limits the ability to resolve fine details. So diffraction happens because light behaves as a wave. So when light passes through an opening, just like the lens of a microscope or a telescope or even the pupil of our eye, it doesn't just travel straight. It spread out a little, and the spreading creates a pattern of light or a dark rings called diffraction pattern. So because of diffraction pattern, the image of a tiny points of light isn't a perfect point. It is a small blurry spot called iridescent. And iridescent, Miss Sunday will going to talk this in details. When two points very close and iridescent overlap, making it hard to tell them apart. Now, let's learn and understand resolution in its relationship to diffraction. So diffraction fundamentally limits the resolution of any imaging system. The amount of diffraction depends on the wavelength of the wave and the size of the aperture. A smaller aperture or a shorter wavelength leads to less diffractions and thus better resolution. So, in other words, diffraction limits the resolution because it causes light from point source to spread out, blurring the image, and no matter how perfect the lens is, diffractions set a fundamental boundary to the finest details you can see. For example, in microscopy, even the perfect lenses, you cannot resolve details smaller than roughly half the wavelengths of the light used. Similarly, large telescopes achieve better resolution mainly by increasing aperture size to diffraction's effect. So the relationship is clear. Diffractions limit the resolutions because it causes spreading of light waves, limiting the resolution of any optical system. And understanding this, it helps us better design instruments and explain why some details remain invisible despite the technological advancement. So now, how do we decide if 2 points or when 2 points are just barely distinguishable? This is where Rayleigh criterions comes in, and Miss Sandy will talk about this in detail.